Okay, so as we've already talked about in the course, keeping track of units is incredibly important, um, and will be something you want to practice in the course. And so we're going to talk about here a technique that is useful in science and engineering for helping to develop relationships and equations in science and engineering. So it's called dimensional analysis, and the idea is that every physical variable is going to have units, and those units can be broken down into some fundamental basic units. And those base units, as we've talked about previously, we have mass, which is in the SI unit is in units of kilograms. We have length, which in the SI system is in the units of meters. We have time, which in the SI unit system of units is the second. We have, what else do we have? We have electric charge, Q, which is in the units of coulombs. Okay, so these base units, M, L, T, and Q, every other unit pretty much can be written as a combination of these base units. Okay, now when we have a line and it just has a length, we would say the distance has dimension L, L standing for the base unit L. If we look at a square up here, this square, okay, has an area of L times L, or L squared. It's a length times a length, so we would indicate that the base units for that are L squared. Volume, length times width times height, and we end up with L cubed. Time has a dimension T, speed has a dimension length per time, or L over T, so on and so forth. This page pretty much summarizes some of the common physical quantities by dimension. So for example, acceleration, which we just talked about this week in class, just started talking about, is a length per time squared. In other words, LT to the minus 2, or meters per second squared for the units for acceleration. Okay, energy is units of mass times length squared per t squared, or ml squared t to the minus 2. Okay, so this is actually one of the quantities that we're going to be interested in this lab. Okay, we're also going to be interested in units of length and time and density. Okay, density is not on this. Well, yes, it is. Density is right here. So we're going to be interested in this quantity. We're going to be interested in length, and we're going to be interested in time. Okay, those are some of the main units or physical quantities that we're going to be interested in this particular case. Now, all are powers of the fundamental dimensions. So again, any physical quantity can be written as a product of these different dimensions raised to a particular power. So in this experiment, you'll take some measurements and you'll do some graphing and analysis, but before you do all that, the first thing you're going to want to do probably, or well, I don't remember where in the process I have this in the procedure, but at some point you're going to have to try to derive the equation for the radius of an atomic bomb fireball. Okay, so when the Trinity experiment was done, that was the experiment that was done as a precursor to the atomic bomb that was developed at the end of World War II. And in this explosion, this atomic explosion, a big fireball is created, and the fireball expands out of the explosion. So you've probably, just from watching movies and things like that, you've kind of experienced that. When an explosion happens, there's this blowing outward type effect. And so we're interested in looking at a series of photographs from that early atomic bomb test, and seeing if we can develop an equation for the radius of that fireball as a function of other variables. Okay, and so what I'm going to describe here over the next few slides is a general method for how we go about doing this, and then I'll give you another example, and then hopefully you'll be able to do this for your experiment this week. Okay, again, the work for this experiment is going to be due on Monday in lecture. I would definitely encourage you to try to work with a partner or partners. No groups bigger than 5. I'll allow you to go up to 5 on this first experiment because you're doing it outside of class. but you typically, again, the lab groups will be no bigger than 3 when we're in the classroom. Okay, so anyway, the general method here is that you select a physical quantity that depends on other physical variables in your problem, and we call this the dependent variable. So for example, perhaps we're interested in the period of an ideal pendulum, simple pendulum. Simple pendulum is just a little mass ball on the end of a very light string, okay, and it swings back and forth. It's a very, very simple idea. As a matter of fact, we usually ignore the mass of the string and just look at a point mass essentially on the end of the string. And so in that particular example, the period is the time it takes for the pendulum to swing back and forth one time, okay? So first thing we do is identify the variable we're interested in. In this particular example that I'm using to guide you through this method, we're going to be interested in the period, the time it takes for a pendulum to swing back and forth. So the second step is we need to think about all of the factors that could influence the physical quantity in which we're interested. We want to list all the variables we believe could be involved. So these variables should be independent of each other. That is, they should not influence each other. Okay, so these are called our independent variables. So for example, with our pendulum example, we might suspect that the length of the pendulum, might have some bearing on how fast it swings back and forth. We might also expect that the mass of the pendulum may have an effect. Obviously, maybe the planet we're on, maybe the pendulum will swing differently on planet Earth than it would on the moon or Jupiter. So the acceleration of gravity for the planet that we're on might affect it. And none of those 3 variables there would influence each other. I mean, if we change the mass of the pendulum, that doesn't change its length or the acceleration of gravity. So those are independent variables. Now we could throw in there air resistance and friction, but things like that. But in the ideal case, we're pretty much ignoring air resistance and friction. We're assuming that it's kind of like an ideal case. So those variables don't have to be included in our particular example here. Okay, so step 3 here, we want to express each variable in our problem in terms of its fundamental mass, length, time, and electric charge dimensions. So in our example here, the pendulum example, we would have L, M, and G as our independent variables, and T as our dependent variable. All right, the period depends on the other 3 variables, and they don't depend on each other. And so what are the units here? As we break it down into base units, the length of the pendulum would be in units of length, L. The mass would be in units of mass, M. Acceleration of gravity, that would be meters per second squared. That's a description of how quickly things fall to the planet's surface that you're on. And we'll learn more about that this semester as we go along. But it would be in units of meters per second squared in the International System of Units. So that would be a length per time squared, or LT to the minus 2. And then, of course, our dependent variable, the period, is in just units of time, T. So we've got our base units there. Now, step 4, write an equation setting the dependent variable equal to the product of the independent variables, each raised to a uniquely assigned exponent. So, for example, in this case, T is our dependent variable. That's going to be equal to the product of each of our independent variables raised to a unique power, or exponent. So I've chosen just x, y, and z as my exponents here. So T, I write the equation here that T, my period, is going to be m to the x times L to the y times g to the z. In other words, I don't know the powers of those yet for those variables, but if I multiply them together with the right powers, I should be able to combine them in a way to get the units that are on the left side of my equation. So I write that equation. Now, step 5, we're going to rewrite that equation, but we're going to use the base units in place of each variable. Then we're going to simplify and combine like variables. So, starting here on this line, in place of T, the period, what are the base units for that? Well, it's T. Okay, it turns out that our period that we define as a T happens to have the same base unit as T. So we have T on the left. Now, under M, M is a unit of mass, so capital M to the x power, right? And then L up here, right here, L is raised to the y power. Well, the units for L, the length of the pendulum, that's the base unit is L, and so we see that raised to the y power down here in this equation. And then we have our G, okay, we have our G, which is our acceleration, to the z power. Well, you know, in G, a G up here at the top of the page, G was LT to the minus 2, so that goes in place of G right there. And now I have in this equation right here, I have the equation kind of rewritten with the base units. Okay, now what I'm going to do is kind of do some math here and combine things. So m to the x I can simplify as just m to the x, L to the y I can simplify as L to the y. In this particular term right here, if you'll notice, what I can do is distribute through the z. So I have L to the z and then t to the minus 2z. Right? When we take something to a power and into another power beyond that, those exponents multiply together there. And so that leaves me with this equation right here. Now, if I look, I've got two like terms. I got an L to the y here, and I've got an L to the z here. Obviously, I can combine those exponents, simplify the equation. And when I do that down here, that tells me that t to the first power. Why did I put a 1 there? Because you know, I want to put an exponent for each thing that's there, and this doesn't have an exponent, which by default means it's 1. So t to the 1 on the left side equals m to the x times L to the y plus z, right? I combined these two, right? And then t to the minus 2z. And now that's simplified, and so this is the equation here that I want to focus on for right now. So I take this equation from the previous side, right? And from the known dimensions on the left side of the equation here in step 6, the dependent variable on the left, from knowing those units, for example, we know time is just the base unit time to the first power. We're going to solve for the unknown exponents on the right side of the equation. So matching things up here, on the left side of the equation, I have t to the first power, and over on the right side, my t is to the minus 2z power. Well, these have to be equal, all right, because my dimensions have to be consistent on both sides of my equation if it's a valid equation. So I write down the equation 1 equals minus 2z, because I know when I'm considering my time dimension, 1 on the left is the time dimension I need for my dependent variable, and on the right I'm told it's minus 2z, so minus 2z must be equal to 1. Now I go on and I consider the unit of mass here, m to the x. On the left, what is m? Nothing. Nothing. It's a 0, right? M to the 0 on the left. That would just be a 1. So my m value on the left is a 0. My value on the right for my exponent for m on the right is x, and so 0 must be equal to x. This tells me that if I'm doing everything right, that the period of the pendulum is not going to depend on the mass of the pendulum bob, okay, which is an interesting discovery here. Now, the last thing is looking at my units of L. On the left, again, nothing there, so by default, my length units on the left are 0. On the right, I have the length is up to the y plus z power. So y plus z must be equal to 0. I write another equation. Considering the units of length, 0 on the left must be equal to y plus z, and I end up with 3 equations with 3 unknowns, and have certainly can solve that. And when I do that, if you do that properly, you end up with, as shown here, you end up with this answer that x equals 0, z equals negative 1/2, and y equals 1/2. Okay? So now what we do, finally, in step 7, is we go back to our original equation, all right, and we express the dependent variable as a function of the independent variables raised to their appropriate powers. Okay, and when we do this, we do want to include a constant of proportionality c, because we don't really know for sure, all right, we don't really know for sure if there's a constant of proportionality in there. So when I go back to my original equation, if you remember, my original equation was t equals m to the x, L to the y, and g to the z. Okay, so all I've done here is rewritten the equation. I've put a constant of proportionality c in there, some independent dimension, is it dimensionless quantity, constant, right? And that squeezes in there. And now I just fill in my powers. I know x is 0, right? I know y is 1/2, and I know g is minus 1/2. And so I go ahead and put all that in, and I get this equation shown right here, on this line here, right? And again, if I simplify it, I could now write it like this. I could say, well, the period of a pendulum then should be equal to some constant, right, or some dimensionless constant times the square root of L over G. And it turns out that's exactly right. The period of a pendulum, simple pendulum, ideal simple pendulum, does not depend on the mass of the pendulum bob. It only depends on the length of the pendulum and the acceleration of gravity on the planet's surface. Okay, turns out that the C value here, the only way you can really determine a constant of proportionality or the dimensionless quantity in these equations is through physical experimentation. And it turns out in our case here, C is 1. And so pretty much we end up with the equation that you'll see in your textbook a little later this semester, towards the end of the semester, T equals the square root of L over G. And so this is how we go about deriving an equation using dimensional analysis. Now, before we continue, I do want to do one more quick example. Let's suppose that we were interested in, it's ice hockey season, right? So let's suppose we are interested in the energy of an ice hockey puck, okay, after it's slapped by a hockey stick. Okay, so the energy of an ice hockey puck in motion. Okay, so in other words, if it hits us, how much energy does it have? You know, energy of an ice hockey puck after it's hit. Okay, and so, you know, that would be our dependent quantity, right? Energy. And what are the units for energy? The units for energy are, let's see, they would be mass length squared per time squared, time to the minus 2. So there's our unit for energy. Now, what would the energy of an ice hockey puck depend on? Well, I could certainly guess. I mean, when I think about the possible independent variables, I certainly would think about the mass of the hockey puck, right? Because obviously if I was shooting a foam puck at somebody and hitting them with it, you know, I would expect the energy that it hits them with to be different depending on the mass of the hockey puck. So I'm going to go ahead and guess that the, and I'll use a small m here to help distinguishing. So mass, m would be the mass of the puck, and that would be, our base unit for that would be, as we talked about, would be m, right? If we look at the base units for that. So we have the base units up here for energy. What else might it depend on? Well, obviously, I think it would make sense that it obviously would depend on the speed at which it's hit. You know, how fast is it going? And, you know, the units for speed would be units of, let's see, meters per second or length per time, right? So there's our unit for speed. And again, if we kind of ignore air resistance, that shouldn't really affect it much. And you know, if it's kind of coming towards me and not being assisted by gravity, we could, you know, if it's kind of like a sideways slap shot, we could probably pretty much ignore the effects of gravity. So that might be just about it, right? So let's go ahead and assume that's the case. Then I would write the energy of the hockey puck is equal to the mass of the hockey puck to the power x times the speed of the hockey puck to the power y. So there's kind of what my equation would be. Now I'm going to write this in base units. So on the left I'm going to have m L to the second power t to the minus 2 equals my power for, or my base unit for m is mass, that's to the x power. Base unit for velocity is length per time, and that's raised to the y power. So now I go ahead and combine these and match things up. So again, simplifying this a little bit, this would be what? M to the x, L to the y, and t to the minus y, I guess is what that is, right? Okay, so on the left, I've got the first power here. Again, it's not shown typically when we have something raised to a first power. We don't list that, but that's essentially a 1 on the left side of the equation there for mass. So here I know then, looking at the mass on the left, I've got a power of 1. That means x over here has to be 1. So first, right out of the gate, I get 1 equals x, and one of my equations is actually solved right out of the gate. Now I look at L, and L here is a 2. That means y over here must be a 2. So L is going to have to be, or I'm sorry, 2 has to be equal to y. And then, let's see here. Okay, well, there we go, right? So what we have here is, that the energy, so let's write this out now, the energy is going to be equal to some constant of proportionality times the mass to the first power times the velocity to the second power. And that's exactly right. We will eventually learn later in the course. If you've had some physics before, you might already know this, but later in the course we will learn that the kinetic energy or energy of motion for an object is 1/2 mv squared. And so we just derived here with this dimensional analysis, another example, we determined that the energy has to be a function of m times v squared. The constant of proportionality in this case actually ends up being 1/2, but there again you see how this method works. Now, what you want to do is work on finding the relationship for the radius of an atomic bomb fireball. Okay, so here's some hints for you, and I think some of this was discussed in the handout I gave you. You should have a lab handout from class on Wednesday, from lecture. If you were not there, the lab document, the handout, is posted in the lab module, same place that you found the link for this video. And you can print that out from a campus computer or your home computer if needed. So hint number one here, so we're going to look, our dependent variable is going to be the radius. We want to know, well, what's that radius going to depend on? Well, if we think about it, obviously, you know, how big that fireball is going to depend on the energy of the explosion. I mean, that's absolutely for sure. Obviously, if it's a bigger energy explosion, the fireball is going to get bigger faster. It's also going to depend, the radius of that fireball is going to depend on the time after the explosion happens. Obviously, if the explosion happened like a microsecond ago, the fireball is not going to be as big as if it happened maybe a second ago. So the time after the explosion happens is going to be a factor or a variable. And then the density of the material that the fireball is exploding into. So some of these early atomic bomb tests, they even did them underwater. So obviously a fireball from an atomic bomb, its radius expanding outward with time, if it's exploded in water, it's not going to expand outward nearly as quickly as if it expands out into something like air. So the density of the air is another possible factor. How dense is the air that the fireball is expanding into? And so let's consider those as our independent variables. Now, second hint I'll give you in this case, because obviously we're not going to experiment with atomic bombs. The constant of proportionality in this case, as was with with our example of the pendulum, is c equals 1. So when you go to do this derivation of the equation, your constant of proportionality is c equals 1. Okay, so you're going to basically go ahead and derive that equation. And after you have achieved your goal, gotten the equation, or obtained what you believe is the correct equation, I want you to check your answer by watching the video, helper video, check your equation, which is posted in the lab module of Canvas also. Check your equation, be sure you have the right equation before continuing with the laboratory activity. Okay? So good luck and have fun. Hopefully you learn some things and it's interesting for you.